afternoon, everyone. I'm Lucia Pallottino. I'm from the University of Pisa. I'm the chair of this keynote speech. So this afternoon, that's the last day of the conference session part. Tomorrow there will be workshops, and this afternoon I'm very happy to present you the next speaker, that is Professor Veronica Santos. She's a mechanical engineering. She got a bachelor degree in UC Berkeley. Then she got a master and a PhD degree at Cornell University. And she also did a postdoc and finally an associate professor, assistant professor, always in mechanical and also in aerospace. And he's a professor, mechanical and aerospace engineering at UCLA. She is the UCLA Samuel School of Engineering Associate Dean for Equity, Diversity, and Inclusion, and Faculty Affairs. And I would like really to mention that she is the first woman who has this role, so I'm very happy for that. Congratulations, Veronica. I think it's a very important thing. She also received many awards, among which I would like to mention the National Science Foundation Faculty Early Career Award. And our research interests are in biomatics of human hands, human-machine systems, and also tactile sensor. We will talk about touch today, and also grasp and manipulation for robots. So the speech of today will be the role of touch in robotics for a connected world. I would like to welcome Professor Santos. Thank you.
Thank you so much. Thank you all for sticking around and showing up after lunch. First, I'd like to begin by thanking the organizers for giving me this opportunity to share our labs, basically our students' work, and to share with you the handful of ways that we think about artificial touch in human-robot systems in a world that is increasingly connected by the internet, but also divided through unequal opportunity, socioeconomic status, and so on. So I'd like to begin with just this array of, showing off how many different groups have created artificial hands that can impressively perform many different complex motions. And if you saw Antonio Bicchi's amazing plenary this morning, then you also saw the soft hand, which sorry I don't have here. But the point is that we have hands that can mimic complex movements of the human hand. And what I would like to challenge you to think about is, what does that movement mean without touch? And so I'm going to start off this talk with a little snippet from a 2015 PBS NewsHour segment on the science of touch. It just so happened that a collaborator of mine, current collaborator, Dustin Tyler at Case Western Reserve University, was in the same segment as my lab, but I'd like to show you the segment from his lab.
Science correspondent Miles O'Brien had much of his left arm amputated last year after an accident while on a reporting trip for the NewsHour. He has since been exploring leaps forward for modern prosthetics.
And feel free to adjust it as needed, okay?
A hand without a sense of touch isn't really a hand at all. It's more like a pair of pliers. Watch blindfolded hand amputee Igor Spedik try to pick up some blocks using a prosthetic without a sense of touch. It's not very productive.
That was no sensation.
No sensation.
And so you were just
going blind.
Just
literally going blind.
Yeah.
Now watch what happens when the sensory perception is turned on. It's like night and day.
But then when I grab it, if I grab it just right, I feel all three fingers. If I grab it right, or two fingers. Then I know I have it, and then I'll move over and drop it.
Is it your phantom hand that you're feeling it in, or is...
Oh, it don't feel phantom to me when I grab a block. To me, it does not. It feels like my hand. It feels like something between my two fingers that's vibrating.
For Igor, who lost his hand in an industrial accident 4 years ago, something powered by a battery and made of plastic, metal, and silicon can become his hand.
So the first concept I want to leave with you is that touch is useful. And in a world where robots are physically manipulating, interacting with their world, whether these are robots that are operating within the human body, intimately attached to, connected to the human body, in very close proximity to the human body to assist with activities of daily living, or in co-manufacturing environments, touch is important, as well as in extreme environments where you don't want to put humans because of the danger, whether it's search and rescue, handling of dangerous materials such as finding buried mines, or operating in glove boxes for nuclear decommissioning and handling of radioactive materials, deep underwater, or in space. And for many of these applications, I like to think of the 80-20 rule. We can do amazing things. So many of the things that we've seen robots do has been driven by vision. But there are maybe 20% of these cases where vision can be obstructed or entirely absent. And that's when I think that complementary senses, such as proprioception, understanding where our limbs are in space and the effort that we're putting in, as well as touch, can help to fill that gap when we don't have that direct line of sight, such as when you're tying your hair behind your head or putting on a bike helmet. Maybe your hand itself is occluding the object that you're manipulating. In other activities of daily living, maybe you're reaching in that dark, fumbling around for that light switch. You're reaching behind obstacles inside your backpacks, but doing it without looking. Right? And now you take it to more extreme environments. Imagine you're in an active wildfire. There's smoke. You have low visibility because you're in turbid water deep in the ocean. And so I kind of showed this going to extreme environments, but you can also think about the challenges for extreme types of objects. And as our field moves away from always considering objects to be rigid to acknowledging that they're deformable, and maybe we don't have perfect models of them, consider deformable linear objects like rope or thin sheets, or even deformable bulk materials such as dough. Now, what if you have deformable materials that are also animate? Right? They're doing things that you weren't expecting. And then I threw an in-hand manipulation here as a grand challenge for many researchers studying grasp and manipulation. So the second point I want to leave you with is that touch is multifaceted. And if you saw the plenary this morning, then you know that there's a beauty to the 2,000 mechanoreceptors that we have in each of our fingertips. I only have this one slide to very briefly show you the complexity here, but you have superficial mechanoreceptors as well as deep. And within those two layers, you also have the fast adapting. These are the types of mechanoreceptors that respond to transients, like slip or vibration associated with texture, as well as the slow adapting mechanoreceptors. They respond to slower, lower frequency change in shape. And we think a lot about that when we consider the deformation of the finger pad and relating that to local geometry. Now, our lab is somewhat agnostic when it comes to the many different types of tactile sensors that you could be using, because I personally don't think that there's any one hand or any one type of tactile sensor to rule them all. I think every application is very unique. You have to consider cost, robustness, form factor. What is the information, the actionable information that you would like your sensor to encode so that you can decode it and make a decision with it? So I'm going to show you over the next few slides a variety of the different tactile sensor embodiments that we've worked with, beginning with some low-cost, wrappable, piezoresistive fabric sensors. We've also looked at embedding barometers inside elastomer. Of course, this is inspired by the work pioneered by Rob Howe and additionally innovated by Matei Ciaucarli. But we also have a collaboration, I have a long-standing collaboration with Jonathan Posner at the University of Washington. And we're making microfluidic tactile sensor skins. And the idea is that you have microfluidic or micro-scale channels that you fill with a liquid metal, and now you have deformable, twistable wires that will never fatigue. And in the image on the left, if you pass the wires over one another, you don't intersect with them, but you pass them over, then there's a dielectric material between them, and where they cross over, you have a single capacitive taxel. And a taxel is like the touch analog to a pixel, if you want to think of it that way. But of course, this only responds to normal forces, and we wanted to extract more information. So we transitioned from a capacitive-based approach to a resistive-based approach. And you can think of the spirals in the lower right-hand corner and the serpentine rectangular shape on the upper right-hand corner, just like liquid metal strain gauges. And what we learned is that you can, if you have the limited real estate of a very small fingertip, you can put normal force spiral taxels in areas where you think you're going to have the most contact. and you can put pairs of these shear force sensors. And actually, we're finding that it often only takes one of these serpentine strain gauges to measure shear in a given direction. So now, if you've got all of these, you have normal and shear force, as well as vibration. So by moving from capacitive to resistive, we ended up being able to measure up to 800 hertz of vibration. And one of the things that we've been doing most recently is taking that multimodal skin and marinizing it for underwater use. And this is in collaboration, again, with Jonathan Posner's team at University of Washington, as well as Andrew Moore at RE2 Robotics, which was recently acquired by Santos Robotics. Now, the image on the left I know is not very pretty, but it's what I'm allowed to show. And it kind of shows the evolution of this skin that we made on the lab bench, and then we tried wrapping it around different form factors. But ultimately, what we're heading towards, again, even on the right, that's not the final fingertip, but you can imagine taking these individual taxels, laying them inside a glove fingertip, and now that glove is slipped over a gripper that then goes deep in the ocean. We also have been working with camera-based elastomeric tactile sensors. Optical tactile sensors are not new. It's just there's a lot of renewed interest because of the advancements that have been made in manufacturing and miniaturization for cell phone cameras and the ability to put these into form factors the size of a finger. So we have a collaboration with Ted Adelson, who helped to invent the gel sight, which is a camera embedded behind an elastomeric finger pad that's illuminated from the inside, and then you can also put an array of markers on the inside and track the optical flow. And so one of the first things we wanted to do was test this tactile sensor in a granular media environment. And I'll come back to the granular media environment later, but one of the things I find so exciting about this is because tactile sensing is traditionally done in an open air environment, where it's very easy to tell the difference between no contact and contact. But as soon as you plunge your sensorized fingers into sand, now you're stimulating everything, and the perception problem becomes one of distinguishing touch that you care about, like contact with a buried object, from all the other noise generated from just moving freely through the sand. And of course, our team has also picked up on the open source MetaDigit design and customized it by adding some finger pad markers on the inside and adapting it to multiple grippers. So the final tactile sensor I'll tell you about is the SynTouch BioTac, and there's a little disclaimer. I worked on this when I was a postdoc at USC with Jerry Loeb. It was funded as part of the DARPA Revolutionizing Prosthetics program. It was intended to be bio-inspired and to go right on prosthetic hands. I also serve on currently on the board of advisors. So this finger has a core, like the rigid bone in your fingertip, an elastomeric skin that's inflated away from the core by a conductive fluid. That finger pad also has fingerprints on it to amplify the vibrations. And on the surface of that core are an array of electrodes. And we use that spatiotemporal changes in those impedance in the electrodes to track how the finger pad is deforming. And if you tap into that fluid volume with an off-the-shelf pressure sensor, you can sample it slowly to measure low-frequency pressure as a crude measure of overall fingertip force, or you can sample up to 2200 hertz and pick up on vibratory signatures. There's also a thermistor in the fingertip that you can use to measure the rate of heat conduction away from the finger to infer material properties. But most of the time, we're using the hydrophone and the impedance electrodes. So far I've shown you the hardware for collecting data, for collecting digital information about mechanical deformation. But we haven't yet abstracted it to things that have meaning that operators might want to use to make decisions. And so the third point is that touch is abstraction. So first of all, you have to perform an action in order to generate tactile sensor data. You don't usually get it for free. So there is, as Dr. Beakey mentioned this morning, there are these sensor-motor contingencies. Action and perception are inextricably linked. Okay, so if I ask you, tell me about the roughness of the chair that you're sitting on right now, what would you be doing? I'm seeing people rubbing their fingers on the chairs. That's exactly right. So there's a seminal paper by Lederman and Klasky from 1987. They were studying the psychophysics of haptic object recognition. And they basically gave their human participants a bunch of objects, asked them to report on different material and shape-related, weight-related properties, and then observed how they used their hands. So for example, if you want to learn about texture, you're probably going to do some kind of stroking or lateral motion. If you want to know about local shape, you're probably going to feel it with your fingertip, follow some contours. If you want to know about rigidity, you're going to press against it. So this idea of exploratory procedures, or EPs, was already in the human literature. And for our first entry out into machine learning, we basically replayed exploratory procedures on a sensorized robot hand. And we started with local geometric features, such as edges, the orientation of the edge with respect to your body. So imagine you're reaching into your pocket, and I'm sure that you can find the corner of your cell phone or the power button on your cell phone all through touch. So we were interested in local geometry, bumps, pits, sizes, shapes, things like that. Now, more recently, we've been thinking about tactile perception of directionality and inferring the direction of a force perturbation on an object that you have grasped. And this is useful if you want to do a handover without looking or set something down without looking at the support surface. And I'll show you a little bit under the hood of this particular project. First, you have to begin by collecting a lot of tactile training data. And instead of perturbing the grasped object, we held the object steady, and then we perturbed the finger relative to that. And then you just have to reverse that relationship. And so you collect hundreds, thousands of these different instances. And then we created tactile images from that finger pad deformation. Again, we focused on the electrode impedance, and we have 19 electrodes to work with, but we knew that they all sat within the same continuous volume of fluid on this, in this finger pad. So we interpolated between them, made a grid so that we could have a square-looking image, and we basically take changes in impedance and map them to grayscale values. Now we have an image that reflects how the finger pad has deformed. And then we use our known directional values, or truth values, for some supervised learning, and train a couple of neural networks to extract the direction as well as some uncertainty about that direction. And this is when it all comes together. Now we can infer real-time tactile directionality during interactions with other agents as well as the environment. In the upper left-hand corner, you're just going to see like a pie, and you're going to see a line moving around, and that line points in the direction that the algorithm is inferring the direction of the perturbation. So this robot was programmed to only release the object when it sensed a perturbation away from its palm, as if someone wanted to pull the object away. And then we also have an example where the robot is setting something down, and as soon as the robot senses an upward force due to the physical interaction between the glass and the table, it's programmed to release the glass. But we have also been working on tactile perception within granular media, and this was one of the setups that we used. Basically, again, sensorize a robot arm, perform exploratory movements, and look at the tactile sensor data that we get, and then perform some mapping between those. And we did this for a variety of different granular media, ranging from coarse sand to fine gravel and coarse gravel in terms of size of the particles. And after training a sensor fusion recurrent neural network, we can basically tell you whether the fingertip is touching something that is buried or freely moving through granular media. So when I hit play, in the lower left-hand corner, you'll see a belief map that's generated from a single exploratory procedure, where red is what the robot thinks is an object, and the blue is where the robot thinks that there's just granular media. And we have a paper in revision right now that's looking at how to optimize the choice of the next exploratory procedure to further reduce uncertainty in a Bayesian Hilbert map in this new paper. So one of the things that we found pretty interesting, we thought it was a liability at first, and then now we kind of think it's an interesting thing, which is when you take a tactile sensor and you put it in a granular media environment, the granular media can act like a liquid or a solid. It depends on how packed the particles are, how forcefully and fast you're moving through those particles. And so as you move your finger through, some particles are going to move out of the way, but there are going to be some particles that are part of this soil failure wedge that moves ahead of the fingertip due to jamming. And when that front of granular media contacts something that's buried, it will actually trick your finger into thinking that you've touched something. But in actuality, it's the granular media particles jamming, forming force chains, and transmitting force from that object that's not even touching your finger all the way back to your finger. And so we thought, okay, this is kind of like using granular media to turn a tactile sensor into a proximity sensor, and you can do SLAM-like things in granular media. And so in this video, in the upper right-hand corner, you have two images that are basically a proxy for fingertip force. It's torque at the base of the finger on top of fingertip biotac force. And then the main video shows in white the particles that are moving, we think are moving ahead of the fingertip. And when that front of particles reaches that blue buried object, you'll start to see an increase in fingertip force even though the fingertip has not contacted the object. And of course, if you account for different granular material properties, you can use the known jamming properties to reduce uncertainty in the belief map. Without also, that also enables you to minimize direct contact with objects that you may not want to touch directly because they're fragile or dangerous. So the next point I want to leave you with is that touch is expensive. From a hardware and student time perspective, it's very hard to collect tactile data. I can't just go on the internet and download millions and millions of images to work with. We actually have to get our robots up and running and wear out tactile sensors, and students put a lot of time in to collect the relatively sparse data that we have to work with. And so I've shown you how we do tactile perception, but I haven't yet shown you how decisions are made. And so what I'm going to show you are two different projects that involve reinforcement learning at various levels of complexity. But reinforcement learning where the robot learns through its own embodiment how to perform hard-to-code tasks. And we're doing this in a model-free way. So the first one is closing a Ziploc bag. So it's the manipulation of an object that is deformable, transparent, and it's a twist on that contour following, traditional contour following task. So we have a robot sensorized with biotacs. We have a video camera set up, but that's only so that we can automate the reward structure. Once the policy has been learned, you can turn that off and perform this task with just proprioception and touch. So the video on the right is just showing that if you took a naive approach and you looked at the angle of the zipper and said, oh, I'll just follow the zipper in a straight line, that does not always work. You really do need some closed-loop tactile perception because the object that you're manipulating is moving every time and changing its state every time that you're moving relative to it. And so we set up a simple reinforcement learning algorithm. Of course, we have to define our states and our rewards, and we did it very simply using our physical intuition. We said, okay, we probably want to keep the contour, the zipper, in the middle of the finger pad, because if it gets too close to the fingertip or too high up, we will lose grasp of the zipper. So let's give rewards for any action that keeps the zipper in that center sweet spot. And then based on some preliminary studies, we had this 5-dimensional action space that's somewhat biased, but these are the only 5 things that the robot can do with each incremental movement. Now, in this study, we were comparing Q-learning as a benchmark to contextual multi-arm bandits, but the point is that we were trying to perform or balance exploration and exploitation while learning this policy in a very resource-conscious manner, because we don't have infinite trials to learn this because it is so expensive to do things with touch. So the upper left-hand image is going to show you what the 19 electrodes are experiencing, whether the finger pad is getting compressed or bulging. On the lower left-hand side, you can track whether a reward is being given and things like that. But it does take a long time, especially with motion planning delays in between each of the different actions. But after you've learned a policy, of course, you can turn off the vision. And we tried testing this learned policy on novel bags. So we used more flexible bags. We had different loading conditions, and we were happy to see that it generalized to some extent. Didn't generalize to wire, as we had hoped, but it did work for other Ziploc bags. Now, the second skill that we recently are publishing on is flipping a notebook page, which is something that I think we all take for granted when we're reading. But the point of this task was not to demonstrate and learn a kinematic trajectory, but to learn what it feels like to do a task in the quote-unquote right way. And we had to artificially decide what was ideal or right in order to specify a reward function. But we wanted to do this as an example of how you could learn to tune dynamic motion primitives using reinforcement learning driven by touch. So this time we used a Canova arm, again sensorized with the BioTac. We had a binder with motion capture markers attached to it. We set up our reward function, and really the creation of the reward function is where the art comes in. It requires physical intuition, some expertise, some preliminary data to understand where the tactile signatures might be hidden in your data. And our reward function was set up to be a function of the internal fluid pressure, the electrode impedance, or how the finger pad is deforming, as well as a penalty if the binder was moved too much. So in this set of videos on the top, I have 3 different cases. The far left is the one that we are artificially calling ideal. It's that semicircular trajectory. It's very smooth. The middle one is a trajectory that causes warping of the page, which feels different, and especially as you turn the page will snap, and that can be sensed at the fingertip as well. And then on the far right, you have an aggressive trajectory that often leads to excessive movement and dragging of the binder. And then on the bottom, what you see are that the top finger and bottom finger in this two-digit grasp are experiencing 2 different things, and each of the electrodes is experiencing something different, and that the subtle differences in how you just turn the page vastly affects the tactile sensor data, enough that we can learn the difference between each of these different trajectories. So again, the left one is the ideal. The middle one, you can see the page getting bent and snapping down, and on the right, that binder is really pulled around. So after we've learned a trajectory, this is just one of the final demonstration videos showing that we can transfer how the learned trajectory on one size page to a different size notebook page, so a slightly different context. And obviously the parameters of your dynamic motion primitive have to change, but they're all driven by some reward function that rewards the ideal way of turning the page, which is minimum page warping and snapping. So on the left-hand column is the very first time out, and so on the lower left-hand corner, you'll see a lot of warping of the large pages, and on the right column, you'll see after a number of policy updates when we've stabilized our policy. And it turns out that our reward function weighted more heavily what it felt like at the fingertips as opposed to the binder movement. So far I've shown you things that robots can do to feel and to use that information to make semi-autonomous decisions, but I haven't told you other things that you can do with these data, which are to share them with human operators. And so via the internet, via direct connection to the human nervous system, you can share touch in whatever manner that you choose. And so this is me a couple days ago testing out the Tactile telerobot. not the greatest looking face there, but clearly I'm concentrating on this very difficult object handover task. And the biotachs on the fingertips of the shadow hand are sending their information about finger pad deformation to the haptics gloves that I'm wearing. So this is the sharing of the sense of touch from the robot to me as the operator. And I thought it'd be nice to kind of bookend the talk with 6 years later, a follow-up on Dustin Tyler's lab. Now he has established the Human Fusions Institute, of which I'm a part, to show you how far they've come with their peripheral nerve interfaces.
Brandon Presswood lost his arm in a workplace accident in 2012 and is also a participant in Tyler's study. He too had surgery connecting his nerves to sensors in the fingertips of a sophisticated prosthetic limb.
Basically, they've mapped where if they put this electrical signal to this contact on the nerve cuff, then that makes me feel a pinprick in my index finger.
But he doesn't even have to wear it to get that feeling.
The fact it's attached to his arm is actually kind of arbitrary. We can put the prosthesis anywhere in the world, and he would still feel like his hand.
Prestwood is trying out the idea with his prosthetic arm mounted across Tyler's lab.
And so now we can extend his capability. We can essentially amplify the person by taking that sense of connection, the sense of touch, and putting it on any machine in any part of the world and bring it back to your nervous system. And then I can connect it to devices that can do far more than my weak biologic system.
So I met Dustin a long time ago when I was a postdoc, and we were both, I was inspired to follow this career path because of my interest in upper limb neuroprosthetics. And years later, we reconnected at a DARPA meeting, and I said, hey, how's your DARPA haptics program going? He said, oh, it's winding down, but I have all of these individuals with limb loss, and they have their peripheral nerve interfaces, and we can stimulate them. And I said, well, that's great, because I have a bunch of robots in my lab with tactile sensors. Can we begin a collaboration? And so that has led to the last part of my talk, which is really about touch as a means for connection. Because most of my career has been spent on thinking about artificial touch from the perspective of just completing a task. What kind of information do you need to complete a task, to complete it efficiently, but without consideration for the social meaning of touch, which I think many of us can appreciate after the pandemic. And the field of afferent touch is hardly new, but it's something that I've been recently getting into, and I'm very excited about as part of a next phase of my career. So touch is connection, whether you're connecting with a newborn in this world, or a partner, a significant other, or even at this conference, right, with the different comfort ribbons, there's still something meaningful in that elbow bump. Otherwise, you wouldn't do it. Even the elbow to elbow, there's some social connection in that physical interaction between humans, and I think that's really interesting. I joined the Human Fusions Institute, and there are other universities involved. It's growing, and if you're interested, please come talk to me after the talk here. But the Human Fusions Institute is dedicated to directly connecting human and robot experiences using what Dr. Tyler's group calls neuroreality, to enable humans to basically embody robots. And I'm not talking about teleoperating robots as a tool, or even as an extension of the body, but actually operating a robot and feeling as if that is you. I mean, that's the dream. And through this collaboration, I've been reading or listening to a lot of audiobooks on consciousness, because I'm trying to keep up with the jargon that the phenomenologists are using when they talk about what it means to be conscious in this world, to be human in this world, or a sensate being in this world. And one of the things that I had heard is that we are all experiencing controlled hallucinations. Right? Our brains are locked in there, and we're doing things, and that's generating stimuli, and we are inferring what we did and connecting that to what we felt. And phenomenologist Anil Seth said, when everyone agrees on the same controlled hallucination, we call that reality. So imagine having a neural reality where you can pipe in whatever you want, hopefully for good purposes, therapeutic purposes, rehabilitative purposes. You can even pipe in a neural reality to augment capabilities. Humans don't have the ability, I don't think, to sense magnetic fields, but if you had a magnetic field sensing apparatus on a robot, you could send that directly to the nervous system and have someone learn from that. So as part of this collaboration, we decided to throw our hat into the ANA Avatar XPRIZE ring, and we began a collaboration and began creating a telerobotic system using teleconferencing software. And so Luis was the lead at Case Western Reserve University in Cleveland. Lionel was the lead at UCLA in my lab. The operator and the user interfaces are all in Cleveland. The sensorized robots are all at UCLA. And this is a video showing Luis and Lionel shaking hands remotely for the first time. And it's not just about the motion of a handshake, but there was touch as well. So this is a bidirectional communication. And the operator is wearing a non-invasive electrotactile glove to receive that tactile feedback.
I can also move it up and down. Could we do a touch test, please? Yeah, thumb, index. Cool.
So there's their handshake.
The recipient and operator can also work collaboratively through the avatar system to perform shared tasks.
Cheers.
It was a very unsatisfying toast because no one actually got, at least Luis didn't get to drink, but we fixed that later. So fast forward a few months, we made it to the XPRIZE semifinals, and that's where most of our team members met for the first time, and it was an amazing bonding experience. I mean, we just gelled, and there was some trial by fire, there was some staying up till 3 a.m. It was good. Probably not for Lionel and Luis, but it was a lot of fun. And this is Dustin Tyler doing some preliminary testing, and the two things that we focused on, in addition to using a robot platform that is human safe, small footprint, easily deployed, was eye contact and touch. Because when we're interacting, I think a lot of the social interaction happens through eye contact, and you know where your hands are, but I'm not really paying attention to what my arms are doing while I'm talking. So we really focused on those two things, even though we were using a robot that we knew was not anthropomorphic.
Yeah, I'd love to. Nice to meet you.
Very nice to meet you as well. Welcome to LA. It's good to see you.
Thank you.
So,
Pleasure to be here.
oh, that's great. So I'm curious to see how well can you move your hand? Can you flex your wrist?
Let's see.
So this is the operator's first time out, just kind of trying out what she's doing with her own body and looking at the response of the robot.
So now
You
you're
can see
supinating. That's good.
her eyes looking at the hand, sometimes looking directly at Dr. Tyler when he's speaking directly to her.
Natural. Awesome. Bring it back. So my job is really easy right now.
So that was the night before actual testing. During the judged testing, we had expert judges, and we purposely made a training paradigm that was very focused on the operator. And so we treated the operator as if they were in Cleveland. We would get them all calibrated to their electrotactile glove. They wore Oculus Quest goggles that had hand tracking built in so that it would be very lightweight and natural for them to control the robot. And then we had them close their eyes and open their eyes, and they would be in the robot in Los Angeles, meeting Dustin, shaking his hand, going through some of the practice tasks. And again, we built our system on the very human-safe Hello Robot mobile cobot platform, but we souped it up with mini binocular camera so that the operator would have depth perception. But also there's something about having those two cameras that makes them look like eyes. And so when I was in the lab and someone would log in from Cleveland, it really felt like suddenly there was this additional presence. And And you could tell when they were looking at you. It's a little unnerving. So, it really does convey a human presence because there's something unique about a human embodying a robot with the natural tremor, natural movements, the fidgeting, as opposed to something that's very smooth and still and pre-programmed. We also added a Tasca prosthetic hand that had some very simple force-sensitive resistors, additionally on the palm, so that we could also stimulate on the palm. So our journey ended at the semifinals, but I'm very pleased with what we did because we got to come together. We had a shared goal across multiple institutions with a hard deadline, and now we are just a really strong collaborative team, and we're pursuing other collaborations in healthcare robotics, manufacturing, and so on. And we were very honored to be part of the dozen of researchers that Cynthia Gorney interviewed across 4 countries as part of her cover story on the power of touch. So if you're at all interested in touch, this should be hitting newsstands any week now. This is the June 2022 issue on the power of touch. Beautiful photographs by Lynn Johnson. And it's not just about task-based touch, but they talk about the social aspects of touch as well. So instead of leaving you with a list of challenges, I thought I would flip it and leave you with some things that I think are very exciting directions that researchers are pursuing related to touch and socio-physical interactions, which I'm newly interested in. So the first one related to touch is, I know there are groups working on combined proximity and tactile sensors, and I think this is a very exciting area. Because you can use cameras, but I think the proximity sensing directly in the fingertip allows you to do a lot of pre-touch planning. And in the same form factor as a tactile sensor, it's very elegant and efficient. I also think that sim to real is, especially for tactile sensing, is sorely needed. Because like I said before, tactile sensor data are very expensive to collect. If we could simulate the contact, the deformation of the finger pad, and learn in simulation, and then transfer that learning to hardware, that would be amazing. Robots for socio-physical interaction. So what you see there is Dr. Alexis Block. She got her PhD with Catherine Kuchenbecker and is a postdoc in my lab, and I just learned that this week they won the best demo at Haptics, so kudos to them. But this is HuggyBot, and this is basically a human-sized haptic interface. This is a robot that invites touch. And so in this particular instantiation, it's an autonomous robot, but you can also imagine an operator remotely logging in and your grandma hugging you from thousands of miles away. And finally, robot avatars that enable inclusion and full participation in society, in the workforce, in the local communities, in schools. And so I heard about this robot cafe in Japan where people with disabilities who are at home can be employees at this cafe. They remotely log in to these robot avatars and they serve customers. And I think that's amazing, and I think that there are more studies that are needed about human-human interactions and human-human social dynamics, but through a robot. Because, in person, you and I, we understand personal boundaries, peripersonal space, the ethics of how you interact with others. But it's different when someone is inside a robot and it's not just a robot that, can be bullied or whatever. There's someone in there. And so I think that studying those human-human interactions through an embodiment that is not flesh and bone is something that is to be looked at. So I would like to sincerely thank our collaborators, especially all the students that did all of this hard work that I presented, as well as our funding agencies. Thank you for your attention.
Thank you, Professor Santos. Very nice presentation. So we have time for questions. So please, if you want to ask questions, you can come here. We have a microphone, and also from abroad, if you have questions, you can write in the chat. I can have a look at them. So please.
Hi, I'm Marlena Frowny from New Mexico State University in Amazon. Thanks so much for that really fascinating talk. I saw that one of the robots that you used wasn't very anthropomorphic, and I think that's really exciting to be able to embody people into less human-like shapes. And so I'm wondering, what's the least anthropomorphic thing that you've seen someone embody into, or what would it be like if someone embodied into a car and could control it haptically? So curious. Thank you.
Yeah, that's an interesting question. My first thought is Transformers, yeah, I think embodying different objects. I think I've seen people wearing things like octopus tentacles and things like that. I think that we're very adaptable and we can learn to use any type of vehicle that we're given to embody, and we'll just play around and figure out all the interesting things that we can do with it. Thank you.
Hi, I'm David Millard. I'm University of Southern California. Thank you for your talk. It was really interesting. I thought it was fascinating how you covered a lot of physical phenomena, so granular materials, interactions with humans, I mean, a little bit squishy in the hands. But at the end you mentioned sort of sim-to-real transfer, and a lot of your work has been very data-driven. Is there something you've identified that's particularly hard to model about touch? Do you have a position on maybe what the bottleneck is here for modeling?
Well, I'm not an expert in contact dynamics, but I understand that it's very difficult, so I think that's one of the things. If you're interacting with a deformable object and you don't have a good model for that, that's also difficult. So we learned the hard way when the pandemic hit and my students were locked out of the lab. I have a project that I didn't present today, but it's on the manipulation of rope, and it's very experimentally driven. And when we could not do those experiments, we had to pivot. And my student was consulting with experts who model deformable linear objects. And what I learned is it seemed like the modeling is all about configuration. If you think about ball joints and links, how do you get a rope into a knot formation or something like that? But not so much about the internal forces within the rope, which is what we were particularly interested in, because visually, as soon as the rope goes taut and is straight, you cannot visually tell the magnitude of the tension inside, which is exactly what we wanted to control. And we were at a loss. And right when we were concluding, well, that's too hard, then our lab opened up again. We went directly back to experiments. So if anyone can crack that nut, that would be wonderful.
Thank you very much.
We have time for a last quick question, so please.
Awesome. Thank you so much for the compelling case about touch. So I'd love to adopt these, but I just worry about the longevity of these interfaces. Can you maybe speak to that?
Are you referring to the sensing hardware or the interfaces with the human body?
Oh, the interfaces between, say, like the finger with the environment.
Oh, yes. Well, they definitely wear out. And that's part of the expensive nature of touch. We actually, our finger pads will grow back if you cut them, or, our skin will grow back if it's damaged. We actually have to replace entire skins when the fingerprints get worn down. So I think, robustness is a problem, but that's with most products in general. And we're so focused on the underlying fundamental research part that we kind of skip over the robustness part. But definitely, there's that the valley from lab to commercial product that will have to be bridged for robustness.
Thanks.
Thank you.
Okay, so we thanks again Professor Santos for his nice presentation.
Thank you.
Very interesting. And thank you all for being here, and I wish you a nice rest of the conference. So